Good afternoon, gentle readers, fellow Earthlings. Today is July 7th, 2024, from Seattle, Washington, at the desk with Ross Finlayson. Here's today's moment in motion. Geometry is motion. Trying to figure out kind of what to address or figure out since last time. It's been about this Zeno swath, the idea being that this cutting edge of the field is associated with how to deliberate upon the infinitely many higher orders of the derivatives of displacement with respect to time that affect anything as a matter of dynamics and changes overall. Has that beyond our current model, which has a model of constant acceleration called one of Newton's laws, force equals mass times acceleration. Whereas you kind of might think of kind of two sets of Newton's laws. The first set of three is, equal and opposite after rest, and motion. And the other one is like that as one. And then force equals mass times acceleration. And then after that, the constant acceleration of gravity and stuff like 22 or 28 feet per second squared and this kind of thing. Gravity on Earth, usually, according to the geodetic survey, the constant varies to a decimal place or two around the world. Not much more than that in most places. They're always trying to figure that out. The geodetic survey carefully goes around the entire world, and in each kind of place tries to measure the force of gravity according to its situation there. So with his swath integral, the idea is trying to figure out for Zeno's arguments, because Zeno's already established that we have at least something like uniform motion, and that it's related to the constant monotone progression of time, which parameterizes all physical processes in a single universe by single universal time, in theories with a clock hypothesis, which not all have, many or most do. It's usually associated with the idea that there's causality, and so with the sum of histories results the sum of potentials, and then according to changes in causality are affected as by intelligence and the ability to act given intelligence to make small changes at critical equilibria, which can result very different outcomes given otherwise the course of events. And so that's related to basically anything that involves deliberation, intelligence, or the process of minimization or maximization, optimization, as it were. So these are the kinds of things I've been trying to figure out for quite a while, because what I want to do is help address the fact that there are these zeroth laws of motion. And it must have this mathematical equipment, this apparatus of the formalism to reflect what are these infinitely many higher orders of acceleration, most of which are pretty close to zero, or pretty much almost all of them are almost nothing, yet that for any given impulse, and it's kind of related to this specific impulse, kind of like point particles quantities are related to the aggregate and flow of these quantities. The impulse overall vis-a-vis the specific impulse, and getting into the quantities of work and power that makes work and these kinds of things, and the physical quantities and all the setups. That is something I would so hope to start with the mathematical requirements and desiderata of being able to explain how there are infinitely many higher orders of acceleration or derivatives of displacement with respect to time that we have in our classical theory, sort of just one of those at a time, and then the entire kind of definition of kinetics is based on kind of trying to figure out how to approach that, when at the same time it's always kind of under quantities, that it breaks down to a finite element analysis, that force equals mass times acceleration is a function of time. So then that's just broken down usually in terms of real analysis, and just integrating and making derivatives of those quantities so associated with it with regards to trying to solve the problems of computing the solutions of what are the expected results given expected inputs, of course with the scientific method, the physical interpretation of the scientific interpretation after the mathematical interpretation of the models of these things, to arrive at ways to thusly equip mathematics with at first the concepts at least, and then the sensibility, fungibility, and tractability, and then physics automatically picking that up because its terms are mathematical physics' terms. And then with regards to the dimensional analysis and all that kind of thing. So here that was reflected a little bit, quite a lot actually, with regards to the linear and the rotational, as with regards to the dimensional and the dimensionless resonator and alternator. These being the ideas that instead of the idea that the body carries as of all the forces around it, that it just kind of moves through space, and then whatever forces it encounters are incident to it. And so this is just a way to get into then this the stop derivative first, which is trying to figure out how power law derivative kind of comes down from infinity and then goes over and then goes all the way down to negative infinity, or vice versa. What it does when that impulse at the origin to basically make it so that that becomes a continuous analog of that usual most particular property of the computation for these extraordinary differentials in the rediffer integral systems, then differ integral in the integral differ systems, integrals and derivatives together, integral equations and differential equations, integral equations and their plane curves, and differential equations and their solutions, complementary duals, singularities to each other, figuring out all these things, because it ends up kind of being one thing. And then so with regards to that, trying to help to first kind of formulate this, to put it into words, and then to kind of formulate this is to put it into formula, is something that I have been looking around a little bit for. And so I'm trying to understand why it's not just a much more regular thing for science to be like, well, how do we do this? Vis-a-vis is like, this is what you do, which is fine for what it is, but it's not so great when we get into these ideas like the pseudomomentum, really, and the theory of potentials, the potential fields of the real fields, really, and these kinds of things. And then this besides, of course, things like, well, our quantum mechanics is like superstring theory. It's got a continuous background. Or our relativity theories are both special relativity and general relativity put together, with general relativity put in front, and then special relativity following from that. But the light-like and special relativity just kind of being free as of information in the spatial, for the spatial. And I got all this from this guy named Einstein, who's out of my later years, really put this together. You know, he's like, hey, I don't know what you've heard about special relativity and general relativity and curved space-time, but there's also one where it's one thing, you know. He helps keep it together. And like quantum mechanics with the stochastic interpretation, it's like, there's not causality. All we can tell is that it behaves like a random probabilistic event. And it's like, well, yeah, it's so fast. You might as well see what kind of, how fast the coin is spinning. I mean, every time you stop to check, it spun 1,000,000 times. So both of those can still be put together pretty well. And with the quantum mechanics and the continuum mechanics and the relativity with space frames, frame spaces, and what we call here space contraction is kind of a unified event, that then this stop derivative and it is supposed to help figure out the pseudo-momentum cases for the stop derivative, walk integral, pause derivative, or pause integral, run derivative. These being the ways these things kind of flow when like one is greater than the other or less, or they're about the same, or there's three, and these kinds of things. This is from mathematics, because these days what's kind of understood a little bit better is that we have for a long time, and we meaning like people who study mathematics, arrived at things like for probability theory, the law of large numbers. The law of large numbers, the classical law of large numbers is for any large number, there's an arbitrarily larger number. And so for any event that's as of a ratio by in a sufficiently large number, there's a sufficiently larger number. So the ratio goes to 0. And so that implements, making for the limit, and because at least something goes to 0, even though it's, a vanishing quantity and this kind of thing. So that's a law of large numbers. Then there are these more laws of large numbers, because in the whole space of the zeros and ones, the Cantor space, the language of 0, 1 in omega many terms, has at least three forms. There's at least these three forms of continuity, Cantor space, and infinity. So at least these three laws of large numbers. And that help to reflect that some things in number theory, like various conjectures of Goldbach, for example, or various conjectures of the similarities theorem and arithmetic progressions, are not decidable. They're independent number theory, because number theory is non-standard, because it's got at least three kinds of infinities, big, bigger, and biggest, here in a sense. So that a lot of the things that end up saying, like, well, we have Grothendieck universes and we have solved the Lagrange problem, is like, well, yeah, and I've just added a zeroth law that makes that a distinctness result instead of a uniqueness result. Knock yourself out, right? And so this kind of amuses me then to get back into the reasons why, that there would be these kinds of alternations, this dimensional alternator, dimensional resonator, that given these various concerns, move back and forth and make it for so that there would be ways to formalize these rules of laws of infinity for these different continuous domains. And in physics and mathematics today, they talk about the quasi-invariant measure theory and the pseudo-differential in the quantum field theory and quantum topology, differential topology and quantum topology. That for function theory and measure theory and topology and questions of continuity and the metrizing ultrafilter and these things in the field of topology, that it's still sort of so that function theory and topology are considered a little looser in terms of which, well, you can pick up topology, or you can find different ways to make a measure for the measure problem and for questions of continuity. That at the same time, that doesn't necessarily become too bad when you kind of are able to put that in theory down below and call the foundations and say, hey, we actually also deconstruct arithmetic and algebra. Geometry is still the same thing, though. Geometry is pretty much where it's at already by itself. But it does have continuity in it, There isn't really such a thing as a disconnected thing in geometry. So but there's the space, because there's a point in space of all the things. The theory kind of has built in that Euclidean geometry just starts with a point, and then a line, and then a plane. But geometry is like, our geometry is point and space, and so it's kind of already both the things from both ends. It's this deconstructive account has got both already, and it's similar with some of these ideas that get into arithmetic and algebra. What about arithmetic? Well, there's infinity or not, yeah, or we'll just have addition and division, two operations instead of addition, it's inverse. Multiplication is repetition, and division, that's inverse. So we'll have two groups kind of resulting each other in the middle, and there's a limit of each other instead of, not really having those decoupled in a sense. So yeah, that there's at least three laws of large numbers, that there's at least three definitions of continuity, that there's at least three kinds of Cantor space, are things that are true in the sense that there's demonstrations of them mathematically. The line rails, firstly, they're mostly the easiest thing to build, and then the field rails just get built up with them with a little formalism. Then the signal rails get involved with all these things like the Fourier series and the implementation of the heat equations solutions and these kinds of things. So, fellow Earthlings, let's see what we have in the books today. This is a Barnes & Noble College Outline series from the 60s called Modern Logic. And what it is it's pretty cool, because what it has is stuff like De Morgan's rules of logic, modus ponens and modus tollens and this kind of thing, ways to make derivations, way to make strokes, those being a way to make a calculus so that you can make symbols of things logically and then just strike through them, and then what remains, or what's still made is as of these symbol scripts, or scripts of Frege or whatever. He made a nice little diagrammatic calculus according to pictorial representations of terms, and it helps to affect to relate them in a way that's not always one-dimensional. And so that then and these days how they do that is called category theory and diagrams, category theory diagrams, which show transitions from place to place, and it basically implement small models of finite state machines, which are usually considered as networks or graphs, where networks or graphs are kind of the same thing mathematically, with regards to networks usually indicating there's flow among the vertices, and graphs variously being directed or undirected, where the vertices go head to tail in one direction, or when they're undirected and when they go in both, and whether they are all just have like a unit weight, or that there's various weights, either dimension, like the cost to go up the hill, the cost to go back down the hill, and these kinds of things, with regards to the very ubiquitous nature of a graph is connecting everything, while at the same time it kind of lives on an integer lattice. And then in quantum mechanics and physics, that's called the field number formalism of basically each point in space-time is living on this one graph that is not a discrete graph, it's a continuous sort of network. So this book is pretty good, though, because it's before kind of the era where it's like, we're going to show you how to do material implication and how to make a quick little scratch pad. So by the time you get out of this course, and it won't take as long to learn, and you won't have to know so much, you'll be able to come out saying you passed a logic course, and being able to write out these things. And given a world of facts, I mean, if the box is closed, then you'll be able to go through all these different facts and write out a quick sketchbook and say, like, you know everything. And so you're able to relay facts as built up about this. This was read out a lot from the Norvig and Russell's artificial intelligence book, where the idea is like, well, how do you make formalized mechanized inference? And it's like, well, you kind of got like a setting here. It was like, well, you're designing a video game, and so it's a grid, and so all the different pitfalls and the gold. And so what you're able to do is indicate by what would be the inference rules that each of these different locations on a grid or graph shows for its neighbors, how to make rules that would give your estimated maximum goal. But you already have to, this is for somebody who already knows everything about it. I mean, it's kind of like given a corpus of facts, you're able to run stuff off about it. But what it doesn't do is, when the terms are free, the point here is that classical quasi-modal logic with material implication, or the fact that not P or Q, it makes for false antecedent or false consequent being materially implied. It's called quasi-modal logic because it's not modal, it's not temporal, and it's fraught with pitfalls. Pitfall was a game, and in it, it's a side-to-side scroller, and you basically have to run through a swamp and jump on the alligators' heads when they're not biting, and then sometimes swing across on a vine, and then other times there's layer 2, which is like underground with ladders, and you run across those and have to jump over the scorpions everywhere. I forget what this was great entertainment, kind of in the realm of Frogger, which was a video game where, as a protagonist of this game, it's a frog trying to cross a road, and either way in both lanes of traffic is traffic going back and forth, or there are lily pads going back and forth. So you either have to stay on the lily pads or stay out of the way of the cars and buses and trains. This was considered high entertainment in the era when the video arcades were a big deal. I liked Arkanoid. Arkanoid is a fun game. And Alcon. That was pretty fun. Alcon, there's a way to pass. I passed Alcon several times. It was probably my main, I suppose, and it's kind of fun. At some point in time, I found it on the MAME emulator, multiple arcade machine emulator, and it was very, very rustic, very nice. So, anyways, going back to this book, this logic is enduring and will always be valid. And what it gets into is such notions as equivalence and tables, some useful things. That is pretty useful. Let's see what he says here. Inference rules. A table of some useful tautologies. Simple implication, modus ponens, modus tollens. Denial of a disjunct, simplification, adjunction, hypothetical syllogism, absurdity, addition, equivalence or double implication, double negation, contraposition, De Morgan's laws, commutative laws, equivalence for implication and disjunction, negation for implication, biconditional sentences. The tautology and the identity and the equality are kind of three same things when you think of them as kind of the same. There are also ways to effectively relate that there are three kind of different things. Similarly with like same and different is like, well, are they same or are they different? Well, are they different like not the same, or are they different like completely different? These kinds of things. And the way this has been used to kind of frame some of these things for the setups is the tendencies and propensities, because there's like an action principle of least action. So a tendency is the idea is like what rises must fall. It's really is the least action. There's nothing going on. Where a propensity is something that's dynamic otherwise. For example, an input or an intelligent event, which is adding an input. A propensity is so driven that acts to create like what would otherwise just be the opposite of a plainly entropic effect. So tendencies and propensities, then in this restitution and oscillation, when things go around and round or back and forth, and attenuation and dissipation where they just go down. So these are kinds of helping to affect to reflect that it's just still the same laws that have that. Then the different open and closedness of the systems is according to these tendencies and propensities and oscillation and restitution and attenuation and dissipation, which all can be just considered one thing. It's just after a sum of history, some potentials, least action. But it's the various ways that it does. So kind of like in physics, then we say, well, energy is the quantity. Everything is energy or equivalent to energy. Well, it's in different forms, mass or charge or light in its flight or neutrons in their lifetime. At least 4 different kinds that help to affect to reflect in. For all the at least 4 different fields of physics, that there's still unification in a sense, but this unification is like, well, if it's one in terms of the other, or if it's another, it's in terms of them. If it's another in terms of them, then it ends up making this threefold way that these 4 quantities are related together. So general relativity generally has, and special relativity too, that this space, like in the time, like in the light, contain matter and then quantities and charge. And so the geodesy is determined pretty much by the space, like of what matters in it. And then, so charge kind of falls out, but at the same time, then charge becomes like the force carrier. And now I know this is coming around a bit, but the point being here that there's no concept at all of the nuclear transmutation, whereas light is this third thing that enters then in the special relativity. But it could be framed in a different way. You could have the nuclear and the optical instead of the massy and the electrical. It would just take so much longer to kind of be worked out that there's not really a history, not really a memory, not really the configuration of experiment in time, that our configuration of experiment, this big science these days, is not really like across 100 miles or 1,000 miles, although in a sense there are many experiments that are, in terms of the sky survey, of course. And they're not so much like, for 1,000 years or 5,000 years. Big science hasn't been around that long. But there is stuff like, in giga electron volts or these kinds of things. So this book is pretty good, actually, and it doesn't really introduce too much nonsense. And it helps to explain a lot of the technical stuff that goes into primitive symbols, well-formed formulas, definitions. So getting into model theory and theory in terms, predicates, and relations in terms of propositions of terms and the relations. And then whether first-order predicate calculus that was what I really thought logic was for a long time, and I still kind of do. But it's a theory of relations, and it's a theory of terms. So when you get into something like Tarski's, like, I just want to have there's no constants, or it's all constants, so I just want terms. It's like, well, really everything's relations, and so when it comes to then the classical, it's all really pretty much predicates. Is what is so, and relating these kinds of things. Logic, propositional calculus, if then and such. The Huntington postulates will now be used for the construction of theorems in the class calculus, as in the propositional calculus. The student may expect to see some theorems that fit well with his intuitive understanding, some theorems that are not at all intuitively evident, and some that are intuitively so obvious that the proof would seem unnecessary to anyone ignorant of the meaning of an axiomatic system. There's just, when there's one theory of all the objects, they all kind of have to be of the theory. It's just a template theory. It's just the meta theory. Whatever there is as a primitive objects basically they seat themselves as the elementary objects of this theory. Terms, predicates, and relations, for example, or physical quantities of these various forms, as was just discussed. Numbers or sets or parts. Any one of these different kinds of putative candidate theories is really having to live in this one universe of theoretical objects, which is like, usually it's full with math and logic, that it kind of works out that the mathematical universe really kind of sits pretty well when you say, well, then we've got set theory. It's a theory with one relation, and then it's got one axiom says, we cannot consider anything that is not regular. But then they got two axioms that indicate regularity. There's well-foundedness, and then there's well-ordering. And they don't always agree, because the ordering is more of a property of the ordinals in the ordering theory, whereas the well-foundedness is a property of like finite numbers and such, which of course is very, very much so regular and rulal. Helping decide that for a law of large numbers is like, well, there might be three laws of large numbers, and that's great, but all we have to do for induction is a law of small numbers. So the deductive inference that gets involved makes it so that it has to become a holistic kind of thing to be thorough and complete. And Gödel very well advises us that any other theory that's strong enough to assert its own consistency is, via induction, incomplete. So our complete theory is available from axiomless natural deduction all by itself, a meta theory template of then for the elements and objects what arises as the thing. Theorems. So he introduced the null class, the universal class. Oh, so that's pretty good. So I'll study this some more because he gets into things like the proposal that there is a second non-identical universal class leads to a contradiction. And that's one of these universals, in the universals and particulars, and specialization and generalization. But that's something I'm much more interested in things like these Huntington theorems than quasi-modal logic, because pretty much anything that's sufficiently complicated to have either end and not just kind of like a beginning and an end kind of a thing, is having that these are objects of it, like a universe of theory, whether that's physical theory or mathematical theory or logical theory. That there is one at all, otherwise there would be more than one, and then those would be in one, so there is one. Blanchet quotes J. Cavailles concerning this point. When the reasoning is written down, the visible structure of the argument will betray any improper steps. This is often familiar to programmers as the great thing that is type safety in strongly typed languages, where the compiler will guarantee that according to these types, according to the relations of types of terms, they're types that the semantics are so. The behavior is defined. This book is Material Science in Space. It's from Halstead Press by Aliyah Regal. And, well, fellow Earthlings, I'm not quite so sure, except that when this book was published some time ago, it was a time when in 1985, a bunch of the experiments that had been done in Skylab and on the Soviet side, whereas with regards to all kinds of the empirical processes of material science known at the time, with regards to metallurgy mostly in space, and that being mostly in the realm of the weightlessness or zero gravity. And here that gets into these things. So this book is really great because what it helps explain is a lot of things to do with what reasons there are experiments in space to determine what would be possible to happen either more cheaply or more inexpensively after the incredible expense of getting something in space, or uniquely in a zero-G environment, microgravity. And one of the big things is Marangoni convection. Marangoni convection is kind of like the capillary action of a sort, and there's much more to be said about it. Marangoni, Marangoni convection, but it's one of the big things in the field of that kind of deal. Anyways, this is a pretty cool book because it helps. It basically is a survey of all the space science experiments from the United States and the Soviet Union through 1985. So. A couple copies of American Mathematical Monthly. I saw these and I picked them up because mostly I had an article on infinitesimals, but then the article is really just kind of a rereading of the hyperreals, which have no real analytical character, and they're just a kind of conservative extension of otherwise the field reals, so they don't really say anything. But there's a great article on the Haar integral, Haar, the Haar integral, and the Haar has got a lot going on, because as I was looking at this, and I'm going to look into it some more. Because this is an issue of American Mathematical Monthly from like 1972 or something like that. And what's in it is this Haar integral on topological rings. And he defines R plus and R star about its additive group and its multiplicative group. And he's breaking it down arithmetically into these two different parts. And so he's got this right Haar integrals, and then talk about the modulus, and then these matrices and stuff. And then the next article is about Gregory's method for numerical integration. But these Haar integrals are something I'm going to look at some more, because they'll have framed up some of this stuff with regards to simple left-right cases that are separable and that otherwise are not tractable, but have very clear and simple things going on with them. A book of Confucius's writings. This is a translation of Confucius, who is one of the principal scholars and philosophers and governors who arrived at the backbone largely of the Chinese spirit today, tempered with Buddhism and if not so much things to do with the dynastism and this kind of thing, and then with regards later to the Cultural Revolution, although a lot of that is very Confucian in its speech, but not so much of Confucianism was not a failed experiment, and Confucius is pretty wise. And then he does have he does have that most people think of the outside of Confucianism is like, obey, and a large part of it is, but then Confucius also has that somebody who's like a realized individual is also he gives a lot of respect to realized individuals. So it's something to say that he says, hey, if you want to go with the flow and stay in the crowd, that's a good idea, and do it, and think and feel that way. But he also says, if you're not going to, then at least be good at it, So Confucius is something that I get a thing that says. He talks about the dynamics of respect, basically, and gives advice like, what a man dislikes in his superiors, let him not display in his own dealings with his inferiors. What he dislikes in his inferiors, let him not display in his service to his superiors. What he dislikes in those in front of him, let him not display towards those behind. What he dislikes in those falling behind, let him not display towards those in front. What he dislikes in those on his right, let him not display it towards those on his left, and what he dislikes in those on his left, and let him not display on those on his right. This is the principle of the measuring square, or foot rule. I haven't heard that one before, but it's kind of like a nice addition to the golden rule. It's like, the do unto others bit is like, do unto others what is the opposite of what you'd rather not have done unto you. Golden rule number 4. Confucius. So this is edited by Lin Yu Tong, and is written from the Modern Library books about probably about 1960. And it indicates some pronunciation guides, and it has a map of China, and otherwise is with regards to that this was of a time. So this is printed in 1938, so before the Cultural Revolution. This I found, and what it is Graustein's higher geometry. And so when I saw this, I was kind of excited because he's an associate professor of mathematics in 1940 at Harvard University. And it says, the principal aim of this book is to initiate the student in the basic ideas and methods of higher geometry. And so this gets into a lot of things that go on in forms that end up being relations that, like, for example, about the convex, or circles that are close to each other in size and proximity, or not. And getting into, besides various theorems, like we were talking about the other day, like the 9-point theorem and the 9-circle theorem and various hypothesis theorems with the 3 crossing lines and the 3 intersecting lines and these kinds of things, helping explain what's going on a lot with geometry with regards to things like the quadrilaterals and triangles, trilaterals. And here with respect to the pencils. So the pencils is a great thing because it's a point of projection. And so when you think of a point of projection, it's like when you learn to draw in perspective. And so learning to draw in perspective is a key exercise that everybody should do, because what it entails is that you're able to put to paper, by learning some rules, that you can apply the measure of the point at infinity to a point of projective infinity in perspective, so that then it's possible to draw that from a given perspective, from a 2D plane, it looks like a given perspective as from a 3-dimensional perspective. And so trying to figure that out with the projective and perspective here in this world where geometry is motion, fellow earthlings, the idea that the pencils here of this higher geometry have a lot going on with helping to relate that geometry is both geometry in its form and proportion and geometry in projection and perspective. So this would be something great to kind of know, And then it get into also there's a lot of the relations between the geometric forms and then the algebraic forms, or the parameterizations. When you say a parameterization of a line, for example, is in a plane or in a space or this or that. About how to make it so, and then things like the hyperbolas and the parabolas or the conic sections have the kind of particulars. And getting into the things, how many parabolas does a pencil of line conics contain? I think it's either one or two. I think solutions are not provided in this. Space geometry, higher geometry. Lines at infinity in inversive plane, 397 and 398. So on page 397, after this chapter is called the circle, he says, these coordinates represent precisely the imaginary points of the lines. Accordingly, we think of the imaginary points on an infinite isotropic of one family of isotropics as lying one each on the finite isotropics of the other family. Corresponding to each finite isotropic, there is created an imaginary point at infinity. Each imaginary point at infinity lies in the corresponding finite isotropic and on no other finite line. The imaginary points at infinity which lie on the finite isotropics of one family of isotropics form with the real point at infinity the infinite isotropic of the other family. So it's got this infinite and imaginary points at infinity. And so when we think about this idea of shrinking the box, which has got like the point at y infinity, the point x infinity, is that oftentimes and mostly the complex numbers are written as of a diagram on the real plane. And so they don't really live on the real plane, but they do have a form that happens to match like so. And so the idea of this imaginary and real point at infinity and then explaining how they relate back and forth gets into some more of these ideas about how to help to describe that geometry has these notions. You wouldn't call it maybe standard because the point in infinity is not a standard number, but it still affects or reflects that these isotropics and their duals have these ways to relate between them, and they exist in this book of higher geometry. The totality of complex points, finite and at infinity, constitutes the complex plane of inversion. So the inversion here is basically reflected as a space inversion, meaning for a unit circle, as a point goes to 0, its inverse is the ratio of that remaining difference over the unit out from that. So when it reaches 0, it's inverted out to infinity. And so that's included in this its sense in this plane of inversion. Through each point of the complex inversive plane, there pass two isotropic lines, one of each kind. So this is something that would help to get into a lot of the vocabulary, which would mostly be the same. I mean, these are still good. And then it would also help to introduce pencils as something to know with regards to the mathematical pencil, geometries. It also arises a lot in the algebraic geometry. So that's something I'll look to study some more later. This one's called formal rings, normal rings. So M.A. Nymark wrote this book. It's from the IBM Research Library at San Jose. And in it, from the Lomonosov State University of Moscow, in 1959, from Groningen, P. Nordhoff, the Nederlanders Press. That in this book printed in 1960, it's about normed rings. So a metric and a norm are two different things. So when you hear about a norm, you're wondering why they're different. It's kind of like this intentionality and extensionality, or the tautologies, identities, and equalities. Three words for the same thing, as long as you don't care the difference. Because a norm and a metric both basically affect to reflect that the distance, a measuring stick is good everywhere, and it's the same size everywhere. But a metric is kind of like, well, from here, from the metric stick from where you're standing is good. And a norm is like, the measuring stick out there is the same one. So it's this near field, far field, or the local and the distant, the local and the global. So metrics and norms are not the same thing. And so that's something to figure out. And then with these normed rings, it could be some particulars that come into this, why this is so, about rings of bounded linear operators in Hilbert space. Now, I'm not too interested in Hilbert space because it kind of seems to be trying to make more ado of the Eulerian Gaussian analysis. And just like from reading from this higher geometry a moment ago, I kind of would like to just have some more of this original analysis and this dimensional analysis as after the identity dimension and into an algebraic geometry more than an algebraic geometry. And it's not that I don't really care for Eulerian Gaussian analysis. It just is what it is. But it's something that gets into where there are things that would be decided by other forms of analysis that aren't decided by the Eulerian Gaussian analysis. And there are things that it leaves open and claims that it solves when that there are things that ends up being higher up in the theory about the analysis. It's like, well, all that was just held up all the way up. And it's like, well, why didn't you tell me before? Because now this piece that's broken here is broken way up here. And it can't be explained by anything except tearing out the entire analysis and putting back in something like that doesn't have the same necessary strengths and weaknesses in their contraposition, in their juxtaposition, that at some point in time I've left bereft something that's needed to be done. So that said, I'd like to very thoroughly know Eulerian Gaussian analysis and its caveats, those warnings that come with the employment of something, because that way I'll have an idea of when something is just not going to fit, why it would not fit. Gelfand, so he's talking about Gelfand, Murray, Hilbert, Murray and von Neumann. His abstract point of view, which turned out to be most fruitful. From this viewpoint, the nature of the elements of the ring does not play any role, so that a normal ring is simply an arbitrary set of elements which forms a ring in the algebraic sense, and which is furthermore provided with a norm which satisfies simple requirements. C is provided with a norm. It's like, well, it's a normed ring. It's like, well, this ring you have arrived at from building it from these algebraic things after the Eulerian Gaussian is not a thing. It's like, we're talking about normed rings. It's like, okay. It's kind of like having freed the geometer from having to do this, but then saying we won't be needing you anymore either. Just to be a little cynical about things, but not really. It's like algebraic geometry really needs kind of both things, but it's definitely got to have geometry. Thus, with the aid of normed rings, a simple proof of the Wiener theorem on trigonometric series was unexpectedly obtained. Simple proofs and generalizations of many theorems of Tauberian type were also obtained, and so on. So that gets into for the Markov processes and the Wiener processes, that there's again like a branch. There's a whole field that relate these things. That Norbert Wiener, besides the whole cybernetics bit, was involved with this kind of these numerical methods up after this analysis is in last time or the time before we were talking about Markov chains. And then got into like these Wiener functionals and so on, and this for the Norbert Wiener. I think it's the same guy. That otherwise, with regards to this is that that's the results that arrive from that, and the results. Some of the results arrive when ready application of resources, and especially when you got a billion of them, you don't have to think of a new way, and just all of a sudden a million new computers arrived. You can just run it on all of them at once. These are the kinds of things that can help to improve things in parallel by providing a plan that's already sort of put together, you know, and divide and conquer this kind of thing, or the embarrassingly parallel linear speedup is at the same time that this is great then, and will help to reflect how some of these ways that the convergence results are built up, because these normed rings will help reflect, like, over time, as this series and this process goes on, that it reaches an equilibrium in the ring. Ring has this very general notion that it goes around the ring, like the ring of integers, usually finite rings. And there's an infinite ring. Does the infinite ring go around? Well, if you imagine, it does, but it would be like going all the way to infinity and coming back down from negative infinity, or -1, and this all the way around. So algebra is groups, and then rings, and then the fields are the very, very, very most usual things, because they affect to reflect, you know, an operation like addition, or the modules, like the even numbers, or rationals. Those are algebra's objects. Another important class of rings, which are no longer commutative, namely rings with involution, was considered in the work by Gelfand and Naimark. In this work, it was shown that under certain natural conditions, every such ring can be isomorphically mapped into a ring of bounded linear operators in the Hilbert space, such that the involution operation goes over into the operation A to A star, where A star is the adjoint operator of A, and the norm goes over into the operator norm. Here, an important role is played by the concept of a positive functional, i.e. a linear functional f in the ring satisfying the condition f star x is greater than or equal to 0. The methods worked out in this paper, and in particular the concept of a positive functional, were used later in the works of Gelfand and Naimark, and in numerous works of other authors in the investigation of rings with involution and in the construction of the theory of representations of such rings. For the particular case of group rings, these methods were used in the investigation of unitary representations of topological groups. So Gelfand, it reminds of like Gelfand and Dickey, and so Feynman, and then quantum diagrams and these kinds of things as well. So the chapters in this book range from chapter 1 through chapter 8, and the sections 1 through 41 read off like linear spaces, topological linear spaces, norm spaces, Hilbert space, integration on locally bicompact spaces, measurable sets, fundamental algebraic concepts, topological rings, normed rings, symmetric rings, realization of a commutative normed ring in the form of a ring of functions, homomorphism and isomorphism of commutative rings, ring boundary. That'll be interesting. 212. Completely symmetric commutative rings, regular rings, completely irregular commutative rings. So these are just all different attributes and properties of otherwise just the object and the geometry or algebra that's got this feature. Representations of symmetric rings, fundamental concepts and propositions of the theory of representations. So that would be another thing, because he's getting to the spectral operators. So we had our involution and the convolution were both things discussed here, and then the idea of the linear operators and then the spectral operators help to reflect that they're kind of two different things. So from a long time ago, there was talk about like the inner and outer products, and then the direct products in the various forms, and then the different operators that result, you know, when it's still of a type, vis-a-vis when it's of a type, but, you know, above or below, according to the units, the quantities, you know, in dimensional analysis of a type. And then with regards to these things here, is about getting into this. This reminds of Neri and the functional analysis, which should be about 10 years after this, about the regular singular integrals and this kind of thing, where the idea is that what carries on is these kinds of analysis are pretty general. So up in the space, then, after figuring out all these different things, then the theorems in the operator calculus start to flow very readily. So this is the idea that up above all this kind of function theory is operator calculus. And so the involution and convolution and methods of transform and all these different kinds of things that end up making applications. Think from like a Kalman filter to like ways to design radio antennas for mobile devices or any of these kinds of things. All kinds of applications in the electrical engineering are built from this kind of signal theory stuff that's built from this information theory stuff that's built from some of these things. Or, you know, you can build it however you want, but these are some ways that they do that. Then the operator calculus is pretty much how that's relayed. So there's another 20 or 25 chapters here. Quite a bit of, mostly about rings. All kinds of stuff. Decomposition of a ring of operators. So that's cool. It's like, well, you got operator theory. It's like, yeah, we got operators of operators. Page 212 is ring boundary. Definition of fundamental properties of the ring boundary. Suppose R is a commutative Banach ring with identity and that R is the space of maximal ideals of the ring R. A closed set F subset R is said to be a determining set if every function xm in the ring R attains its maximum absolute value at some point of the set F. Evidently, at least one determining set exists, namely R itself. A determining set is said to be minimal if none of its proper closed subsets is a determining set. A minimal determining set is called a ring boundary of the space R. Now, what I'll relate this to is when I was discussing topology the other day, we were discussing topology and what is a continuous topology. Because there's a variety of notions of what is a topology in mathematics, and it's most usually always in the standard linear curriculum in the open topology. And so the idea was that there's initial and final topologies for a topology. And that's basically just like, well, the first thing that is, and when it's no different than the topology under any different changes, anything else would be less. So this is initial and final. So the idea is that a continuous topology is its own initial and final topology. You can't remove it. It would make a cut. You can't add anything to it. It's full. So the continuous topology this way is kind of well defined, sitting next to continuous domain and kind of continuous space too. This kind of thing. Well, those were the books I got since last time, and then what we've been reading last time was this collocation methods, which is the idea of how to make it so that there could be an approximation of this way to make it so that the swath integral is this collocation of these for this two-dimensional system. It's a three-dimensional system, which results as of a sort of in a one-dimensional result, and so that is described as numerical methods to arrive at that, because there aren't symbolic methods. There isn't one given to solve this kind of thing. And so really, this then also gets related to things like annealing and the swath integral, and also some other of the relevant important notions from the non-standard analysis. And here, though, with regards to looking for the closed forms in that, and with the idea that there's at least these three laws of large numbers and at least three definitions of Cantor space, pretty much according to these laws of large numbers, and big, bigger, and biggest for infinity, at least three kinds of one infinity. And so that has, then when those sit in the theory together, then the idea is how to figure that out. When already this one theory has to fit all together at the same time, numbering and ordering, numbering and counting, sets and parts and numbers, objects arithmetic, addition and division, vis-a-vis addition and division, and all one thing. Three different continuous domains, the line reals, segment by segment, the field reals after those are all done, and the signal reals when you break one down and make a very, very fine comb of it, Nyquist and Shannon, three different definitions of continuous domains. that these, although they become standard as of the non-standard in the day, they become standard as of the superstandard, and it's the way. Well, all right, I shall so hope you had a nice day, fellow Earthlings. And what I shall also hope to find to help improve the dialectic of the infinitely many derivatives of position with respect to time that mathematics owes physics to help explain any change in classical mechanics at all, and that otherwise that force is a function of time, is that I'll look to find out some more about that with regards to then that it helps to fit together with otherwise this theory forming together is quite a thoroughly complete and consistent theory, and then even for physics too, a thoroughly kind of unified theory, which obviously for mathematics and logic's sake would have to meet all such matters of definition and rigor, and for all such matters of physics' sake would have to meet all such matters of science and the data, of which there's a lot. Good luck, gentle readers.